Now we'll work through this quiz, which is about buckling in columns. And in the first 5 questions, we just go through a few basics about beams and columns and buckling. And now we arrive here at question 6, where we're going to start finding some numbers. We have a situation with a steel column. Here's a steel column. It's a wide flange, 8 by 31, so an 8-inch wide flange by 31 pounds per foot, and it's 24 feet long. Okay, and we're going to find out how big is the critical buckling load, and then how big is the stress when you reach that buckling load. But first, in this step, we want to convert this 24-foot length into inches. So what is 24 times 12? I believe it's 288. Now that we know it's 288 inches, so we have all our units in inches, let's look at the slenderness ratio. Is it slender enough that it will buckle or could buckle? This is a steel column, so we're going to use this formula, length divided by radius of gyration. And if it's greater than 140, it will buckle, given enough load. So radius of gyration, we're going to have to look that up in our table. And we're looking for the radius of gyration around the weak direction. Where is it most vulnerable to buckling? Well, that's around this y-axis. This is a handout. I think you've gotten this before, but you have it again with this set of slides. It's part of the steel manual that deals with 8-inch wide flange. And here in the bottom, about 3/4 of the way down, is the 8 by 31 wide flange. In the next slide, I've zoomed in on that 8 by 31 part. So we want to look at what is happening in the weak direction, which is around the y-axis. And let's find the radius of gyration, the r, around the y-axis. And here it is, r for radius of gyration. Here is the number for our 8 by 31 size of wide flange. So our radius of gyration is 2.02. So the question is, if you take 288 inches divided by 2.02, do you get a number that's greater than 140? Surprise, yes you do. So this column can fail by buckling. That number is greater than 140. So now you know it can fail by buckling. Now we'll look at how big a load will it take for it to buckle. How big is the critical buckling load? And the formula for critical buckling load, we could use either one of these versions that we want. And what do we know? We know the length. We don't know moment of inertia, but we could look it up. We don't know area, but we could look it up. We do know modulus of elasticity. It's 29 million psi. And we do know the radius of gyration. And we're trying to find P crit, the critical buckling load. So we got 2 different versions of formula here. In either version, we're going to have to look something up. In the first version, we'll have to look up moment of inertia. In the second version, we'll have to look up area. But I notice that the second version is just slightly more complicated than the first one, because you've got a fraction in the denominator. So I would vote for using the first version of the P crit formula, this one here, to keep it a little bit simpler. So that means we need to look up moment of inertia. And again, we're thinking about what is the weakest direction, the most likely to fail, so that would be the y-axis. And here is a an enlarged version of the part of our handout again that deals with 8 by 31 wide flange. And we are thinking about the weak axis, so the y-axis. And let's find the moment of inertia around the y-axis for this beam. And there it is. Our moment of inertia in that direction is 37.1. Okay, so now we can fill in some more about what we know, what is given. It's an 8 by 31. We know the length is 288. Now we know the moment of inertia is 37.1. And we still know the modulus of elasticity is 29 million psi. So let's plug all those numbers into this p crit formula. It starts with pi squared. Pi is such a magical number. And I don't mean that in a dorky way. I just mean it's a wonderful number that is universal throughout nature, and it does all kinds of things. Anyhow, here's our formula, and here we're plugging in the numbers. So there's the pi squared, and it's pi that's squared, not anything else. Then here's our modulus of elasticity. That's 29 million, and if you prefer, you can just punch 29,000,000 into your calculator if that's more comfortable. And then here is the moment of inertia, 37.1. Now I've labeled the units, but this doesn't mean this inches cubed is the units it is in. That doesn't mean you cube anything. Don't do anything with that exponent. Just plug in the numbers. Pi squared, 29 million, 37.1, that's it. And then that's all divided by the length squared, so 288 squared. And we'll get some big number. You should get a critical buckling load of 128,000 pounds. All right. So now, if that's the load at which it will buckle, might be interesting to know how big is the stress at that particular load. And now we go back to basics. Our good old stress equation that we started working with at the beginning of the term. Stress is force over area. Yay! I feel good going back to that one. So do we know the force? Yeah! The force is our critical buckling load, 128,000 pounds. Do we know the area? No, we don't, but we can look that up. So here's where we are so far. Stress is 128,000 divided by area. Let's look up the area, and again we have a wide flange, 8 by 31, so we can look up the area using our steel table. Again, I've zoomed in closely on the part of the table that we're interested in. By the way, this is just an aside, but years ago, decades ago, when I took strength of materials, I had a professor who was always saying, so now you look up the number that you're interested in, and I was sitting in the class thinking, I'm not interested in that number. But anyway, let's pretend that we are interested in that number. So 8 by 31, here is the area, and there's the area of that 8 by 31. Its cross-sectional area, if you look at a slice of that steel, it has an area of 9.13 square inches. That's its area. All right, so what do we know? It's an 8 by 31 wide flange. It's got an area of 9.13 square inches. It's got a load, a force of 128,000 pounds. And we want to know how big is the stress. So we've got a force of 128,000 pounds. We've got an area of 9.13 square inches. Right off the bat, you can see, oh good, our stress is going to be in units of pounds per square inch psi, just like we expect. And if you take 128,000 divided by 9.13, I think you will come up with just a little over 14,000 psi, something like 14,020 psi. That is the stress in the steel at that point. And what we know about mild steel tells us that, that is a stress that is below the yield point of mild steel, isn't it? So yield point of mild steel is 36,000 psi. Even with the AISC factor of safety, the yield stress, the allowable stress would be 21,600, but we are getting a stress of only 14,020. So the stress at this buckling load is going to be less than the yield stress, which is interesting.